Good morning, everybody. Today, we've got a Codeforces round. It's round 728. We also have a brand new awesome background, which hopefully you'll see if we get at least one problem here. So let's jump into the contest. If we can. And here we go. Alright. Maybe we can go to m1.codeforces.com. If you missed the video of me making this background, by the way, I would highly recommend watching it because it is maybe one of the best videos I've ever made. I guess we'll see. Alright, Farmer John has a farm that consists of N pastures connected by one directional road. Each road has a weight representing the time it takes to go across the road. Roads could have negative weight, or you go back in time. However, Farmer John guarantees it's possible for a cow to get stuck in a time loop, but they can go infinitely back in time. Unfortunately, Farmer John has lost the map of the farm. All he remembers is an array D, where DI is the smallest amount of time to take the cows to reach the ith pasture from pasture 1, using a sequence of roads. The cost of his farm is the sum of weights of each road, and he wants to know the minimal cost of a farm that is consistent with his memory. So sort them, and then the edges forward minus the sum of edges backwards. Oh boy. Oh boy. Oh boy. Let's delete them. Okay, thank you. Come on. Alright, let's read problem B then. Problem B. Given a tree of n nodes, you want to generate an array from the tree by marking the nodes one by one. Initially, when no nodes are marked, a node is equally probably chosen, marking the entire tree. After that, until all nodes are marked, a node is equally probably chosen from the marked set of unmarked nodes with at least one edge. The final array is the node's labels in the order it takes the time to reach each node. Okay. Find the expected number of inversions in the array that is generated by the tree in the aforementioned process. I see. Small bounds. Alright, so for problem A, it's a multi-test case. Yeah, so we have int n equals this, int array A, int array size n. Come on. Quit building my workspace. Let me edit the code. Thank you. Let's sort the array. Long ans equals 0. Okay, so we add in all these differences because we need all these edges. And then long n b4 equals 0, long sum b4 equals 0. So then n b4 plus plus, sum b4 plus equals 8i minus 1. And then ans plus equals 8i times n b4 minus sum b4. Test cases, 10 to the 4, I think we should be fine. 9, 0. Oh, minus equals this. -3, 0, 0. Okay, submit a we have longs, right? Yeah, should be good. All right, let's move on to B. So this many nodes in the tree. All right, look at that. Look at that. Beautiful. Absolutely beautiful. I love it. Really just terrific. Is it going to turn off too? There you go. It turns off. Oh, so good. Test in production, ladies and gentlemen. No, don't actually do that. That's bad. It's, I'm a competent software developer. All right, tree array. So we've got this tree. And wait, so what does this array look like? The nodes labels in the order of time they're marked. Yeah, so like well, okay, can we do this for each pair? Can we say for some pair, what's the chance that it'll happen? We've got like some pair of nodes. If we need A before B. So if anything's picked in one of these subtrees, it's going to be A. If anything's picked in one of these subtrees, it's going to be B. Otherwise, we just care about the things on the path. For each thing on the path, we need to pick. So we need to pick 3 things from A, and then 1 or 2 things from B. We want to do this in like order 1, 3 from A, 1 or 2 from B. I guess we could do a DP table for that. So DP, A side, and then B side. So the idea is brute force, brute force the pair. And now we need, okay, yeah, then we do 2 BFSs. 1 from each thing. So it's going to be n cubed times 2 is our runtime, which we shouldn't have an issue with because it's a tree. And then we say, and for each node, then we brute force the 3rd node, like the start node. And then we want to say, like find like the thing on the path. So find closest on path. And then we want to do like some DP. Yeah, like some DP. All right, we can do this easily, I think. Let's jump in for that. So first we're going to want a node. Well, first we're going to want math. Let's do math first. So static long add. so return A times B mod, static long how we have the half power, and then if x mod 2 equals 0, return half squared, else return half by base. Alright, then static long pre-comp. Oh, we also need mod inverse. Static long inverse long x, return tau x to the mod minus 2. Alright, pre-comp, so we need static long array facts, and new long array 1. Pre-comp, this is a void. No, we should be good there. Okay, so we have all of our math. So then we want an int dist. Yeah, in public node. Also an ID. This.id is their ID. What do we need here? We don't need multi-test case. And we need all of the edges, so node array nodes. And we'll read in all the nodes, and then for each edge, we'll say nodes at A dot JSON dot add nodes at B, and then vice versa. Okay, so what do we do now? We need to brute force the endpoints. So for we want every pair. Yeah. Well, I guess we just do this. I guess. So then we'll probably want dist1 and then dist2 as well. Static void BFS, node array nodes, and then node from. Okay, so for node n in nodes, n dot dist1 equals -1, and then from that dist1 equals 0. dist1 equals -1, then nn.dist1 equals next.dist1 plus 1, and then we also need to add it to the BFS. So then BFS.add last nn. And then return, well, we don't need to return anything. Okay, so now we need to BFS from nodes from end 2 for node nn nodes, nn.dist2 equals nn.dist1, and then BFS from end 1. Now we have these distances set. Good, so now we need to calculate this dp. What is the dp? So it's dp at dp at the number of so it's like dp long side or like good side, and then it's like extras. Okay, and then this is equal to the number, I guess the total number of ways of picking this. Equals the chance. Alright, we'll do that separately. Okay. So now we want like diameter between these two nodes will be end1.dist2, and then we say, okay, now we need to subtract from this. So node, I guess n equals nodes of k. So int kdist will be nn.dist1 plus nn.dist2. And then we're going to overcount by quite a bit. So int2 sub will be kdist minus diam over 2. Okay, so now nn.dist1 minus equals to sub, and then nn.dist2 minus equals to sub. Okay, so then we want to say if dist, or if nn.dist1 equals 0, long expected inversions equals 0. This out expected inversions. Just do this under mod just to be safe. So if the distance to node nn.dist1, yeah, so if we are the smaller node, oh, okay, so we want so now if this dist2 equals 0, then expected inversions equals add expected inversions 1. Right, 100% chance. Otherwise, then we want some static int count ways, int n good, int n bad. I guess this will be a long. Oh, so I guess we just put the DP here then. Okay. So if n good equals 0, return 1. If n bad equals 0, return 0. Static long half equals inverse of 2. Otherwise, return multiply half by count ways of n good minus 1 and bad plus count ways n good and bad minus 1. Yeah, so okay, I guess we can add these then. Then we need a DP, static long array DP. DP at n good, n bad is not equal to 0. Then return DP at n good, n bad. Otherwise, return this equals our answer. Alright, so we should be good here. So then we just want expected inversions equals add expected inversions to count ways. How many good ones are there? This is nn.dist2 and n.dist1. Yep, alright. Samples. Oh, no, we need to fill this with -1. Yeah, okay. So now DP equals new long array n plus 1 by n plus 1. Oh, this is BFS is broken. Yep. So BFS.add from. At node 2, the distances are 0 and 1. Oh, do we need to? Okay, so we don't want to do this. I guess, what if the array looks like, if it looks like this, the expected answer is 1/2. Right? Yeah, expected answer is 1/2. Oh, we have to divide by, what are we dividing by? By this, right? Yeah, divide by and choose 2. So n choose 2 is n times n plus 1 over 2. Oh wait, why? Oh, divide by n. Because this is, yeah, divide by n. 5,004 times 2 would be 10 to the 9 plus 8, so that's 1. Yep. Okay, so then do we get this right then? No. Okay. For 0, 1, so what does this tree look like? We have 0, 1, 2. All right, 0, 1. The distance is, well, when it's 0, it's 0 and 1. Yep. When it's 1, it's 1 and 0. The number of ways. it's 0, 0, and 1. Wait, for real? I is 0. Yeah, distance to 0 is 0. This is 1. When I is 1, distance to 0 is 1. So there's one way to get an inversion. When I is 2, there is 0 ways to get an inversion. So we have 0 ways, 1 way. So that's 1/3. Yeah. Plus 1/3. Oh, this is wrong. How are there -1 ways? So 1 and 2. Not equal to -1. Yeah. Okay. Good. Took way too long, but we're finally there. Okay. And then don't print half. $5,009, 5,007. Submit to problem B. Okay, submit please. And then we can move on to the next problem while we wait for it to be showered in some lights. Let's see. All right, the only difference is that, here we go, we got it. Look at that. I dig it. Okay. In this version, q equals 1. You can make hacks only if both versions are solved. There is a process that takes place on arrays. Well, how are the standings looking? Not terrible, not terrible. Okay. Yeah, not bad. There's a process that takes place on arrays A and B of length n and n-1 respectively. The process is an infinite sequence of operations. Each operation is as follows. First, choose a random integer, then simultaneously set AI to whichever is smaller. AI or, oh, so you can optionally add, wait, what is going on? So either make it itself or average it with the thing after it and the other thing. All right, I'm gonna get some water. I'm very confused. task is, okay, so you're given these two arrays, and then you do an infinite number of operations, and then basically they converge. So then they converge to real numbers. Okay. So now you're given B, which is like what you subtract or add. So you're given the some array B, which is like kind of matters here, and also some array C, and you want to count how many arrays A consist of only integers less than each part of the bound. But what is F? Return the value A1 converges to after the process. Okay. This array is good if it contains only integers and satisfies something, and it's small enough. Okay. Count the number of good arrays where this value is greater than x for different values of x. Oh my goodness, this is so complicated. Okay, what is even the difference? Q equals 1. Oh. Oh. Okay. Is this 10 to the 5th or something then? Okay, I don't even know what's going on here. So, what does this even look like? Okay. Yeah, let's just do a couple things so we can understand what this process actually is, like what is going on here. So let's say we have some array. Well, okay, so we have some array, like we have like A0, A1, A2, and then we have B1 between those, or B0 between these two, and then B1 between these two. So now we pick a random adjacent pair. So let's say we pick this pair here. Then we say the min. Okay, so this one gets set to the min. Oh, and this one gets set to the max. Gotcha. So I see. Okay, so the sum stays the same is the first observation, right? So we average these two. Yeah, and then we subtract BI here and add BI here. Okay. Oh, so it's the average minus BI, and this is the average plus BI. Okay. So average minus B1, and then average plus B1. Unless they already differ by more than that. Okay, so you have like a bunch of things, right? And then repeatedly, wait, this converges? How does this converge? Might not converge. Does it definitely converge? It can be proven this converges. For real? Oh yeah, I guess, right? So, like what you're doing is like if you have two adjacent things, first you average them, and then you make the second one bigger by some amount, right? So then you like swap, like you average them but bias it toward the right one. So after they've converged, this array is going to be increasing. Is each step going to differ by BI? Well, not necessarily. Will it? Okay, so if we have like 4, 10, then this will be like 3.5, 4.5, 10. Oh, I see. Okay. So you can have these cutoffs. So B is fixed, so we can abuse that. Or I guess we need to abuse that. So this is the cutoff. The cutoffs are fixed. And then each A is capped. Now we need to count the number of good arrays. So yeah, you can't really shuffle the values very easily. Oh, also all the values are small. Okay, well x1 is never going to be bigger than 10 to the 5th. It's never going to be bigger than 100, right? Because the first element never gets bigger. Yeah, so we can ignore that. Will it ever be less than 0? It could be. Each of the BI's are positive, or 0. So yes, the array is always increasing. Okay, so we only care about places where there are like split points in this array. If there are no split points, then we know like every element except for the offsets, and the offsets are determined by the sum. Yeah. So we're interested in where there are split points in this array. So now the follow-up question is when, like, what defines a split point? Or I guess I know what defines it. A split point is when after you do all your operations, you have some difference bigger than BI. But like the question is when will that happen? Like what kind of conditions are there where you can do a bunch of operations and then be left with stuff with this big difference? So like you've got some stuff here and some stuff here. You do some operations. Will anything ever not be a multiple of 2? So what am I saying? If everything is even numbers, then this is going to work out? No. No. Yes. No. If you have 4, 6, you average them, so now you have 5, 5, and then after that you have a 4. Then you have, yeah, doesn't work. Okay. So the non-integer part of this problem is going to be annoying at best. So we want to know when the average is greater than or equal to x. We can kind of add 1 to everything in A, but it modifies everything in B. So I guess it's a bit tricky. You know the start value, if you have that plus B, that doesn't change the average at all. If you do plus greater than B, then you've just like wasted extra space. Like then it doesn't affect the prefix. The issue is if you do plus less than B, because then this will push you down a little bit. Like it'll push the average down. So it gets spread out equally, right? If you lower yourself by 1, that'll get spread out equally. Yeah. So it's like so this ends up being well, what does it end up being? So it's 1 lower than where it should be. So you lower this by 1/3, this by 1/3, and this by 1/3. So now it's like here, here, here. Yeah, I guess that makes sense. Okay, so we know like the total amount we can give up, I guess. 10 to the 7 dp. So we can have like a dp at position, and then number we can give up, and equals the number of ways. Then we have a big transition though. Uh-oh. Maybe it's a predictable transition. Yeah, it's a range sum transition. Yeah, it's a range sum. Let's, it's hard to read. I don't think it's actually that hard to do, but it's just, I don't know. Honestly, I'm not really that much of a fan of this problem. It's like just difficult to understand. It's difficult to understand. It's not that fun. You don't feel smart when you solve it. You know, just overall, not a fan. Okay, anyway, let's try it. So we'll do the naive DP first and then try and optimize it. How about that? Is this gonna work in the version 2? No, it's not. So we'll have to write something else for the hard version. Okay, so n, and then we have C. What is C? C is the maximum of the A arrays, and then we have B. Okay. One test case. So we have these arrays. We need our, let's just copy this. And then presumably the same mod. I'll double check in a minute. Modulo, give me a mod. Where's the mod? Okay. All right, so we have all of these things. So now we need our DP. So static long DP. So we need a int position. Oh. Yeah. It's not n give up, really. It's like our average. Yeah, okay. All right, figure this out. Okay, so need more paper. Have I? Has this been my face the entire time? Bro. Hang on, let me check. Can I read this while I'm okay? Well, I guess we'll see. Well. So we have some prefix. Oh, really? This it just adds more to the amount. Because if we're going from left to right, then we know like an over increase is not a problem. Yeah. So naively, we need a DP of the position, and then we need the expected value. I guess position and then number we have to spare. Assuming it was like bottom level stuff. So how many positions are there? Oh, this can actually increase. Yeah. Okay, so there are 100 positions, right? Okay, get rid of this, please. We have 100 positions. The C values are the caps. What's the maximum you could spare? So if all the B's were 0, and this was just 10 to the 5th, then it would be 10 to the 5th times 100. Okay, so it's a little over 10 to the 7. It's like 10 to the 7 plus 10 to the 5 or something. It's like 10 to the 7 plus 10 to the 4, maybe even? Yeah, it's a small value. But that's a big number. 100 by 10 to the 7, that's big. Oh, all the things in A have to be at least 0. Okay, what if instead of the number to spare, we store the sum? We store the prefix sum. Then that's only 10 to the 4. We can calculate the number to spare from that. Yeah. Okay, so if we have the position and the prefix sum, we want to place a bunch of things. Yeah, so we have like a minimum prefix sum for each index. So we have DP position prefix sum. For each index, we have a minimum prefix sum that it has to be. Can't ever go under that. Yeah. And then we get to choose any integer to add to it. So go to and then like prefix sum plus x to prefix sum plus. Yeah, okay, so that's a range sum. Any other constraints we're missing here? I don't think so. Okay, let's code it up. So in position, and prefix sum. So then we need a static final int array min prefix sum for position. So min prefix sum for a position equals new int array of size n. Yeah. Not a final int array, just an int array. Okay, and then we're given the number of queries. So now we need the last value. Yeah. So last value equals min start. So the previous prefix sum plus this value. Yeah. Okay. These values are each like 100, so they shouldn't be too big. So we have this, okay. So int biggest place is a max's at position. And then, yeah, so we just place between 0 and biggest place. So now in smallest place equals math.max of 0, and min prefix sum at position for this position minus the prefix sum. So if smallest place is greater than biggest place, then we just need to return 0. There are no ways of doing it. If position equals a max's dot length, return 1. Otherwise, we need a range sum. So for so now ants plus equals, well, add ants to EP position plus 1, prefix sum plus to place. Prefix sum 0. Does this work? Wait a minute, does this work? Hold up. 56. Okay, what is the runtime? Well, it's exponential. So if we memorize it, let's memorize it first. Well, let's not memorize it. So we have 100 positions. We have how many prefix sums? 1,000? 10 to the 4. So this is, they're 10 to the 6 things, this is called. And it goes 100 deep. Transition is order 100. So the runtime is just 10 to the 8. Yeah. Okay, so if we memorize this, then it's just quick, right? Then it's just quick, right? Static long array BP equals new long array by 101 by 1001. So there's that. So now we don't need this pre-comp. Well, we're not even, wait, did I even call pre-comp? I didn't even use it. Good. Okay. Yeah, so we should be fine there. I think that's okay. So let's submit it. I should be submitting in Java 8. Okay, that's fine. 5-second time, I'm worried. Okay, so for C2, what do we do here? Is that the next thing to work on? Maybe. We're not doing too bad. 26th place? I don't know. Could be worse, right? How my friends doing? Where are all my friends? What are they? Is it too late? I guess it is a really late contest, to be fair. A lot of people have work and school and stuff. Okay, let's read D. If it's geometry, we're doing D. Please be geometry. Please, it doesn't look like geometry. Is E geometry? Impossible in Java. Calling it right now. Yeah, okay. So you're playing with a permutation of size n, but you lost it in Blair, Alabama. Oops. I hate when I lose my permutations of size n in Blair, Alabama. It's the worst. Ugh, yuck. Luckily, you remember some information about the permutation. More specifically, you remember an array B of length n, where bi is the number of indices j. Whoa. Where number of indices j, the things before you, okay, so it's like the number of inversions in a prefix. Yeah. You have the array B, you want to find the permutation. However, your memory is imperfect and you constantly change the values of B as you learn more. For the next Q seconds, you can realize that it's equal to X, or find the value of PI. If there is only one answer, print, or if there's more than one answer, print any. Are there ever multiple answers? Well, I like this. This feels like more of a data structure Z problem. The first one feels like, I don't even know. What is C2? So it's like, how many inversions in a prefix? Oh, well, wait. It can't decrease. Or BI is the number of indices J. Oh, not in a prefix. It's like the number of inversions where this is the smaller thing. So it's the number of things before you that are bigger than you. Yeah, okay. How many things before you are bigger than you? So it's how many things before you are bigger than you, and then what is this thing? Or what might this thing be? This seems right up my alley, to be honest. I really like this problem. The other one seems that the numbers are too small. Small numbers are very scary in general, because it means lots of stuff can happen, right? But for big numbers, you know, it's like come up with an idea, then make it like n log squared or something. Plus, the point differential here is enormous. If we get this, it's amazing payout. If we get this, it's just So let's go for D. I mean, we're already sitting, yeah, we're already not doing terribly. I'm fine with this. But if we get D, that'd be huge. Okay, how many things before you are bigger than you? So yeah, there's always at least one answer. Is X is less than I? Yeah, X less than I. Okay, makes sense. So yeah, it's like if you do some stuff, blah, 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 of the things before you, you get inserted into that. Okay, so we could like convert the problem to you get inserted at this position repeatedly, right? So you've got like you have like a set, and it's like insert into this position, this position, this position, this position. So it's like then you're like, okay, insert yourself into this position. Okay, now insert yourself into this position. Are these queries online? Offline queries, let's go. Parallel binary search, I'm calling it. No, I mean, honestly, it feels like that's the solution. So, like, Suppose you know what's the question? What's 2? Find the value of the ith index. Yeah, so find out where it got put. Am I thinking about this right? So it's like, okay, you have a number. You don't know what your number is yet because you don't know how many things get put lower than you. Now you put some other number lower than you because there are 0 things before it. Now you put some number higher than that. Okay, and at the end you have 2, 1, 3. Yeah, so find out where you got put. Yeah, okay, so you know how many things come before you. Yeah, so you need to know how many things come before you and then how many things after then you come before you. So we need, I mean, there are a bunch of ways of doing this, but we can do like a 2D seg tree. Can we do a 2D seg tree? You can't do 2D range update point query. Probably not, yeah, it's probably too hard. Okay, so we can't do a 2D seg tree, so that's out. But this is the classic. This feels a lot like this one Polish lights problem, where you're turning on lights and then like the lights turn on other lights, and you're given, it's like it looks like a geometry problem, but it's not actually geometry. It's just 2 permutations. It's a 3-letter acronym title. I don't remember exactly what it is, but like I remember what the problem is. I don't remember what the title is because it's a Polish word. I think maybe STA, if I remember correctly, but that could be something completely different. It feels like that sort of thing. I guess I'm just talking about parallel binary search. Okay, stop talking. Figure out the solution. Yeah, so oh wait, parallel binary search is tough because the array changes. So maybe not. You have initial memory, you have a point set, and then, okay, yeah. Yeah, so, okay, so we'll go through time, and now we're at some position, and we need to say, yeah, okay, so now we say, is it less than, like, are there X things on in front of me? Right, if we know what everything is, what do we need to do to check me? We need to say how many things in front are less than me. Oh, and the after part is tough because everything can change really quick. What if we store what if we knew? If we knew the answer, then I guess then we're set, right? Then anything after us is fine. Yeah, but we can't really do that many optimizations here because the array changes. Like the fact that changing just one number can screw up the entire structure. So like with just one query, they can ruin our life if we're basing something on like the structure of the array. Besides, the structure of the array isn't actually that complicated. The hard part is just the changing part. Yeah, so maybe I should just stop it with this whole idea. It's such a good problem though. Man, you've got this trashy problem C and this amazing problem D, and I just want to solve D. I don't want to go back to C. Okay. Lost my permutation in Blair, Alabama. Oh no. Can we do like a square root n shenanigans? We got a small n and a big time limit. Okay, so if we build it after n queries, so let's say we like rebuild n log n after square root. So now we have a few changes to the array. We have the array and then a couple changes. What happens when we do a change? So it's like change this to this. That changes literally everything. Oh yeah, we could split up in the next square queries. Make a block for each of them. Yeah, so it's n root n log n. Yeah. Okay. Well, each block is size 350, right? It's close. It's close. Yeah, that's one thing we can do. For these TLEs. Wrong answer, TLE. C2 might be the play. How good is this guy? He's good. He's good. Yeah, C2. Okay, so, well, or do we have a solution here? If we have a solution to D, maybe we should just do it. So, like, the idea is after square root blocks. So, okay, so we're going to handle square root n blocks at a time. Yeah. So now we're handling root n queries, and the array is going to get a bit messed up, but whatever. So now we have a bunch of sections. So now we have root n. We have root n groups. Because these are like the things we set. Things can switch groups. Can I switch groups? Yeah, I mean, you can do an n root n log n. It's ugly, though. All right, maybe we won't be able to implement that. Maybe it's not actually as amazing of a problem as I thought. C2. Okay. C2's got to be fun to do, right? Because otherwise, why would anyone put this in the problem set? Because it's a dumb problem. I'll stop roasting C2 now. I'm sorry. Okay, so... Yeah, what was this? So we just need to do a DP where it's position and then prefix sum. Okay. Problem is, this is a 10 to the 6th state. And now we've just lost the bigger part of the state. We've lost the 10 to the 4th part of the state. Does this actually need to be 10 to the 5th? If it's negative 10 to the 5th, is it ever not going to be possible? No. Right? So if x is greater than 0, then the answer... If x is greater than 0... If x is greater than ci... Greater than ci... then it's 100% of the arrays. Then it's all arrays. No, JK, it's no arrays. It's greater than C0. Then the answer is 0. If x is less than some number, like 10 to the 4, negative 10 to the 4. Right, like what's the biggest this can be? So all arrays would have to be 0, and then all b's would have to be 100. And it would be like, yeah, it's like 10 to the 4 over 2. If it's less than like about 10 to the 4 over 2, then the answer is everything. So x isn't actually that big. X is like 10 to the 4. So can we just make our dp fast enough? X is 10 to the 4, so we're doing this 10 to the 4 times. So we need a 10 to the 4 or faster dp. Or just something we can reuse would be nice too. So if we had a position, dp, position, yeah, the number to spare. I have to go to the bathroom. I think there's a little bit of information overlap here. We're storing the prefix sum. If instead of the prefix sum we store like the number we have left, yeah. Like the value increases, we've got like an increasing floor. Yeah, so we can store dp of which position we're at and the min prefix sum of the suffix. Okay, but the problem is we also need the last element. Because if we jump by too much, oh wait. If we jump by too much, is that a problem? No, it's not a problem. Is it a problem? I don't know. There might be intermittent. Oh yeah, if we know the min prefix sum of the suffix, then we know we know what the prefix sum of each other position would be. Yeah, because everything else has like some required prefix sum. Okay, so we should be able to get this in 30 minutes, I think. So this is, the position is going to be 100 big. The min prefix sum of the suffix, or like the min prefix sum of what's left. I guess this is just min prefix sum of the entire thing. No, it's got to be min, because we need to know what we've used. Yeah, so we have to know the min prefix sum of the suffix. Wait, do we though? Like, there can be gaps. This is like the min prefix sum of the suffix if there are no gaps. Well, okay, it's 100, 100, and then yeah, 10 to the 4. But there's an offset here, so it should be, we can make it linear. What's our memory limit? Probably big enough. Ah. Not big enough even. So we have like a DP, the position, and the prefix sum. And then we have like some min requirements. So we need the DP, the prefix sum, and also like the minimum the prefix sum ever was. And this would be static. So this is 100. The prefix sum is 10 to the 4. The minimum it ever was, I guess the min difference would be 10 to the 4. It's too big. I don't see it. Tourist isn't even solving D. Maybe he's going after E. Possible. Wait, is tourist really not solving D? Come on, bro. You can do it. I believe you. What's up here? TLE and wrong answers. Square root stuff is not passing. Okay. Oh, wait a minute. Yeah. Okay, so wait. Look at the I guess not. Never mind. I was going to say there are only 100 positions of X that matter, but I think there are 100 squared. Because X is the cumulative sum. X depends on the cumulative sum. And if everything's 0 or everything's 100, that's 2, yeah. 10,000. Can't even do a query times 10 to the 4th dp because the queries are so expensive. Wait, is it just offsetting the prefix? The prefix can never be, yeah, so you make everything smaller. All of the requirements. Yeah, these all shift by a constant. Because it's all dependent on the previous one, which is eventually dependent on the start. Yeah, it's tricky. I don't know what to do. I don't know, I'd be happy with a plus whatever. Might end up being like plus 10 by the end of contest. I'm fine with that. I wish I got this though, obviously. Just if only for the ego boost of doing it. How are you guys not solving B and C? You can do it. Man, the UCF sloths over here. Come on. Anderson, please, you can do it. You can do B, Anderson. Yeah, you can do this. This is easy. Easy. Yeah, I don't know. I don't know what to do here. I don't know what to try. Okay, so here's what's going to happen. I have a meeting at 11, which is a bit unfortunate. Yeah, so I don't really have time, as unfortunate as it is, because the contest started so late. If I keep working on this till the end of contest, I wouldn't have time to be able to do solutions before I go to my meeting. So I think I'm just going to do solutions here. And that way, you guys get solutions for A, B, and C. A, B, and C1 at least. Let's look at the Div2 contest, I guess. Yeah, so I can do everything but E2 in Div2 probably. Let's read these. N cats in a line numbered 1 to N with the ith cat at position I. They're bored of gyrating in the same spot all day, so they decide to reorder themselves such that no cat is in the same place as before. They're also lazy. They want to minimize the total distance that they move. Help them decide which cat should be at which position after the reordering. Yeah, so pretty sure. You can swap every pair, which works unless it's odd. If it's odd, you need to rotate a group of 3. So then take the group of 3 and rotate it. That's A. I'll do that. I'll explain it a little bit better in a moment. Count the number of pairs where I is less than j, and the product is equal to the sum. Now, the product of the values is equal to the sum of these. Okay. Gotcha. The sum of the values of the indices. Okay. Interesting. Yeah, so if you have like a 2 here, then if you multiply it by 2, by 3, 4, 5, 6. Oh, I guess, yeah, so always look at the, like, assume you're the bigger of the pair. So you can do it in n times square root n. Yeah, I think that's the solution. Okay. All right, let's do solutions. All right, so let's start with Div2A. What do you say? So I haven't actually solved this, I've just read it, but I can talk about it here. You have n cats in a line, and you want to reorder them such that no cat is in the same position it was before, but also the total distance all cats move is as small as possible. So initially you start out with something like this, and what you can do is, let's say there are an even number of cats. Well, each cat has to move at least 1 position, so we can make that happen by swapping them like this. So we pair them up and then swap them, so then we have 2, 1, 4, 3. So that's a solution if n is even. And obviously that's the smallest possible answer. If n is odd, that means, well, you can't really do that, right? You can't pair them up. So I guess the example where n is odd is if we have a 5 here. So we can still pair up these two, but then we have this group of 3 left over, and then we can do something like this. So we can make a cycle of size 3. So then when we're done, it'll look like 2, 1, 5, 3, 4. And yeah, that's the general idea. So you have to casework whether n is even or odd, but other than that, just pair up everything except for the last 3. And then if you wind up with 2, then you do a cycle of size 2. If you wind up with 3, you do a cycle of size 3. So a little bit of casework, but not too bad. Okay, so that's Div2A. Let's talk about Div2B. So, yeah, pleasant pairs. Okay, so we've got some array. Let's look at this array and input 3, 1, 5, 9, 2. And the positions are 1, 2, 3, 4, 5. So we want to know if there's a product of, like in this case, 3 times 1 is equal to 1 plus 2. Yeah. So here's the thing. If for each element, right, let's say we're some number, let's say we're a 7. What we can do is look through all of the numbers less than 7 that might be some position in the array. Right? So we can look through like 7 times 7, 7 times 6, 7 times 5, 7 times 4, and so on. Now, the key thing to remember here is you might be like, oh, well, that could be n squared, right? Because each number could look through a whole lot of things. But you know that you are the bigger of the two, and you also know the product here is less than or equal to about like 4 times 10 to the 5th, right? The product, or the sum of the two indices, because that's what we're trying to equal. So, yeah, so really, this is like square root of 10 to the 5th about. They're about square root of 10 to the 5th things this could be. And of course, you want to bound it at like 350, right? Don't start at something higher than 350 because 350 squared is bigger than 10 to the 5th. Or it might be a little bit bigger than that. It might be like 500. But yeah, if you started at 500, then it's 500 times n, which I think should be fast enough, right? 500 times n would be a 10 to the 8th runtime, but all the operations are very quick. And then in order to checksum pair, you just need to see, okay, so 7 times 7 is 49, right? Maybe my index is 5, so you want to look at index 49 minus 5. That would be index 44. You want to see if that thing is a 7. So yeah, you just check all of them naively, and that'll solve it probably fast enough. I don't think there's a faster way of doing it, but there might be. I think it would be more difficult to code though. So yeah, I guess I'll do one example here, because I know if you're struggling with Div2B, that solution may have been a little high level for you. So okay, so we'll do an example. So we're going to iterate through every number in this array. So we'll start with the 3. We'll do the 3 as an example. So we're going to try 3 times 3, 3 times 2, and 3 times 1. 3 times 3 is equal to 9. Well, 9 is too big, right? I guess 9 isn't too big, but if 9 minus 1 is what the other index would have to be, and that's 8, which is too big. So this can't work. What about 3 times 2? Well, 3 times 2 is equal to 6. So, and we're index 1, right? So the other index would have to be 6 minus 1, which is equal to 5. Which means this pair, it does work, right? Because at index 5 is the 2. So this works. So we found one pair here. What about 3 times 1? Well, 3 times 1 is equal to 3. We're index 1, which means the other index has to be 2. So if you look at index 2, you get the 1. So that works. You also want to bound this at like 500. I think it's 500 anyway. It might be a little more, a little less, but I think 500 should be fine, I think. I don't know. I'd have to do the math on paper first. But yeah, that way your runtime stays reasonably fast. But like all of the things here are, you do one multiply, you do a subtraction, and then an array access. So you can definitely do 10 to the 8 of those in a second and be fine. Okay, that's Div2B. Now we're moving on to Div2C or Div1A. Okay. Create graphs. Yeah. So for this problem, you know the minimum distance to every node in a graph, in a directional graph. And then you want to say what's the minimum sum of edges. So here's the thing. So maybe we have this, which has an edge to this. This is distance 0, obviously. This is distance 2, and this is distance 3. And there's some edges in this graph. They're all directed. You want to know the minimum sum of edges. The first thing we can do is, well, we can't add any edges that would make these distances too small, right? So we can't add an edge here of like any negative distance or of distance 0. Because if you can reach this in distance 2, then you can reach this in distance 2 as well. So we have a bound on what these distances can be at best, right? The smallest value, or sorry, yeah, we have a bound on the smallest value they can be. But there are some important things here, which is the bound on this edge here is negative. This can be up to -3. So any negative edges, obviously, we'll add those, because why not, right? It'll help us. So we'll add these. And we won't actually add them, but we'll consider what their sum would be in a moment. And then the other part of this that we need is we need to make sure the minimum distances are actually possible. So to do that, we can add the edges like this. So we can add 0 to this of size 2 and this of size 1. The best way of doing this is if we just sort them. Then we have 0, 2, and 3. So we have these sorted numbers. We want to add edges like this. These will be positive, so we would like to not add these, but we have to because graph has to be connected. And then we get, since these are sorted in ascending order, all of the edges going back, oops, that's the same edge twice, all of these edges, these are all negative or 0, so we want to add all these edges, so we do. So now we need to calculate this fast, and we can't just do this naively because there are n squared over 2-ish edges, red edges here, so those are going to be too expensive. So what we need to do is figure out a better, faster way of calculating that. And we can do this pretty easily. So this 3, right, it's going to have a back edge to everything before it. So we can store the sum of everything before it and the number of times 3 will have a back edge. So we're going to do like, basically, yeah, we're going to do 3 minus 2, and then we're going to do 3 minus 0. So if we store, we might have 3 minus some other stuff here, right? So we have 3 minus a whole other column. So we store what is the sum of all of these things over here, and then also how many 3s are there. And we can get the sum of everything. It's like 3 times the number of 3s minus the sum of everything else. And that's the total weight of all back edges. And then we want to subtract that, obviously, because those are all negative. Yeah, so that's the idea. I'll show the code in just a moment here. Code looks like this. Yeah. So we sort the array. If you're using Java, don't use arrays.sort because you'll get roasted by the quicksort break case. Either in hacks or you'll fail system tests. So that's very dangerous, yeah. Then you store the answer, which is just the sum of all the edges, the number of things before you, and then also the sum of everything before you. Then you iterate through the array. The answer, you have to add this blue edge, right? This is the edge we talked about that's going to be positive, so that everything stays connected. And then there's one more thing before you, right, which is the thing right before you, and then you add that thing to the sum of things before you. And then finally, you add the sum of all red edges before you, just like I talked about earlier. So that's the solution to Div1A or Div2C. Let's move on to Div2D or Div1B. Okay, so in this problem, yeah, you've got some tree. You're going to pick a node on the tree, move around a little bit, and then that'll be some new node that you pick. And you want to know what is the expected number of inversions in the array, where the array is just the nodes that you pick in the order you pick them. So let me give some example. Maybe your tree looks like this. You're going to pick some random start node. Maybe you pick this node as your start node. Coincidentally, looks like the root of the tree, but it could be any node. Then the next node you pick will be a random thing adjacent to everything you've picked. So you can't pick this one or this one next, is what I mean. But you can pick this one or this one. Maybe we pick this one. Then the next thing we pick is a random thing adjacent to any of them. So any of the white nodes are adjacent to at least one red node. We pick this one. Then maybe we pick this one and then this one. That's some ordering. So the order would be, let's give these labels. Maybe it's 3, 1, 2, 4, 5. The order we picked them was first we picked this. So there would be 3. Then we picked the 1. Then we picked the 2, and then the 5, and then the 4. So this would be our array. And inversion in an array is a pair of numbers that are in the wrong order, right? So here we have a 3 that comes before 1, but 3 is bigger than 1, so you've got 1 inversion here. You've got a 3 is bigger than the 2 and comes before it, and then you have the 5 is bigger than the 4 and comes before it. So this has 3 inversions. Now you want to know, on average, what's the average number of inversions in this array? Yeah, okay, so that's the idea. So I guess one important part of this is you need to understand what this p times q under mod means. And if you're confused about that, I have a algorithms thread video on what this means and why you can do division under mod. So it's one of the earlier algorithms thread videos. You can look it up on my YouTube channel. And it's like, I think it's called division under mod. And it explains how you can do operations with this. But basically, you just can multiply and divide fractions as if they're just integers. Okay, so how do you do this? Well, let's look at it in a slightly different way. Let's say we have some pair of nodes. Right? The key thing here is the bounds are really small, so we can do some slow stuff. But let's look at this pair. We have this node A, this node B. And then we have some other nodes that might come out of this subtree. They might come out of this subtree. Maybe they come over here. So let's consider all of the possible places we might start. So if we start at this node here, we know we're going to pick A before B, right? So if A's index is less than B, if A is like a 3 and B is a 7 or something, then this won't cause an inversion at all. If B's index is bigger, it definitely will. But in this case, like, this will not contribute. This will contribute 0 to our answer. If we start here, then this will contribute 1 to our answer because we have to spread out from this one node. We're going to hit B before we hit A. So this will always contribute to the answer. If we have something in the middle, though, if we start here maybe, that's a bit more tricky because this could hit either B or A first. It depends how it spreads out. So obviously, we don't really care how it spreads out below this point in the tree. We only care when it hits the path from B to A. When it hits this path, then we care, okay, it's going to spread left and it's going to spread right. There might be other stuff on this path, like over here. We don't care about this either. We only care about this one direct path from B to A. So to do that, what we can do is say it's got one node to spread here, and then it has 2 nodes to spread here. We said A was 3 and B was 7, right? So this causes an inversion if it hits B first. So we need to say, okay, what is the chance that it'll hit the 7 before it hits the 3? And we're only looking at this particular inversion. It might start, like it might create other inversions with other pairs of nodes, but we're just looking at this inversion first. And we're going to look at the contribution of this inversion, and we're going to look at it for all inversions. We're going to sum it across everything. Yeah, so for this particular inversion, we want to know what's the chance we hit the 7 before the 3. Now this is a difficult problem to solve. As far as I know, you can't really do it in linear time, or in constant time, I mean. But you can do it in n squared. And the key thing to note here is we don't care about what these 3 nodes are, because then we would have to do it a bunch. We only care about these 2 distances. We care about this 2 and this 1. So we can do a dp, where we say dp, and then we say, like, what is the distance to B? And then what's the distance to A? And this dp will equal what's the chance we hit B first? The transition is obviously we either need to color one node closer to B or color one node closer to A. So that's our transition. We can reuse this dp across this brute force that we're doing of brute forcing what inversion is it and what node do we start at. So since we can reuse this, the total runtime will be n cubed, like plus this n squared dp. So yeah, since we can reuse this, it's not n cubed times n squared, it's just n cubed plus n squared. Yeah, that's the solution. That's the idea. Why is it n cubed? Well, we brute force the start. We brute force this inversion that we're considering. So we brute force the 2 nodes we're looking at, and we want to know what's the chance one node gets hit before the other. And then we're going to brute force where it starts. And then we say if it starts here, and this is the inversion we're considering, what's the chance that this happens? Now, I guess one last part that I should mention is we need to divide by n, right? And the reason, sorry, I said right, that's obnoxious. I can't stand it when other people do that. When they say right after every sentence, it's like, yeah, but we need to divide by n. The reason we need to do this, of course, is because there's a 1 in n chance that it actually starts here. So we'll find the sum across all starting points, but there's a 1 in n chance that that is the real starting point. So if we just add it, then we'll be off by a factor of n. It's one of the bugs I had. Okay, so yeah, what does that look like? We need a BFS. I guess there's one last part which I should talk about. Let me get some cleaner area to do that. If you have this, so this is A and this is B. If you know the distance between A and B, in this case it's 4, and you know this distance to A is 4 and this distance to B is also 4, you can find for this node, you can find this distance and this distance really easily. So like if this is the node, the start node you're considering, you can say, well, you know this number plus this number, it's equal to this number at this edge here, right? And for each edge we go down, you add 1 to each of these. So you take this 4, right? Like, so the sum should be equal to 4, but it's equal to 8, which means you've overshot by 2. Because every time you go down, the sum of both of these increases. So you do like 8 minus 4 over 2. That's how much each of these are too big by. So then really, if you were to move this to this node here, then it would be 2 and 2. Right? You subtract the 2 from both of these. Okay, sorry, that might not have been necessary, but I think it's helpful. Okay. Where am I? Over here. Okay, let's look at the code real quick, and then we'll go on to C. So, yeah, here's the idea. We read in the tree, and then we fill in this DP. What does a DP look like? DP is super easy. We store 1/2 under mod. This is just 5 times 10 to the 7 plus 4, right? Because, no, yeah. 5 times 10 to the 8 plus 4. Because 2 times 10 to the 9, sorry, 10 to the 9 plus 7 divided by 2. I don't know, it doesn't matter. This is the mod inverse of 2. Okay, anyway, moving on. If there are no good spots left, this means we're at the good side, which means we're going to create an inversion. If there are no bad spots left, we won't create an inversion. Otherwise, these are the 2 possibilities, and there's a 1/2 chance each of them happens. So there you go. That's that TP. So this is the DP for, yeah, if you're in the middle, which one do you go to? Other than that, we brute force the pair, right? So we're saying we're going from I to j, and after we do that, we get the distance from every node to node I and to node j, and then we're going to brute force the starting point here. So at the end, we divide by n, but we brute force this starting node, and we know the distance if you move to the closest point to the 2 nodes, right? You move to the path. That'll give us this here. We need to count the number of ways that this will end up hitting the thing that causes the inversion, the bigger of the 2, which is j. The number of ways it'll hit j relative to the other way, to node I. So this is like the proportion, like the chance that happens. Yeah, so in other words, we're brute forcing the pair, then we brute force the start point. We say, if we have the start point, what's the chance it causes an inversion? What's the chance it causes this inversion? And then we sum that across all inversions, and then print the answer at the end. Okay, cool. 5 minutes left to explain problem E1. Gotcha. So the problem is kind of difficult to understand, but let me explain the general idea behind the solution here. Yeah, so it looks like this. So this is Div2E1 or Div1C1. So you've got like some initial array, and then what one of the changes looks like is first you set these both, like, you're only going to increase this one. So you only do the operation if it increases the right of the 2 elements. But then what you do is initially you set them, like you take their average like this, and then you say, okay, their average needs to be offset by some amount, right? So this amount is a constant that's different for each pair of indices. Which means after you've done this operation an infinite number of times, the array will be increasing or constant at each pair of positions. So it'll be like this, and then you know the average of the array will stay the same. And then you know each of these pairs, it'll either be like the BI, or it'll be the difference in like the averages, right? So either like this will have some really small average and this will have some really big average, and you'll never actually do the operation across this pair. That's what it looks like. The key observation here, though, at least for E1, is that if we go from the left, it doesn't really actually matter that if there are these like jumps in averages, right? If this gap in the convergent array is bigger than BI, it doesn't really matter if we're doing it from left to right, because we know all of these things, like we're gonna place some position such that it doesn't make the starting position too small. Then if this has a gap, it's not going to actually affect this. So we don't need to worry about there being a gap. We can consider we just push this up instead. That's an equivalent way of looking at the problem. So if we are just going to push this up, we don't need to worry about the min and the max part. We can just ignore that because we know the stuff before it wasn't going to be too small on its own. And now adding this stuff, either it'll pull it down, in which case the max part won't matter, or it'll pull it up, but it won't make the answer go from invalid to valid, right? If it pulls it up, the answer started valid, so it'll be fine then. Yeah, that's the main idea here, after you just understand the problem, which is definitely the hardest part of C1. So yeah, how do you actually implement this? Well, let's say we know that this has to have a prefix sum of at least some value, right? The first index needs some prefix sum. The next index has to have a prefix sum plus whatever the minimum value was here plus bi, right? So basically what we'll do is we'll consider what's the smallest possible starting value. Maybe it's like -10. And then we have this bi, right? So we know after it converges, the minimum this thing can be, maybe this bi is like 2. The minimum this can be is like -8, right? And then we have this bi is maybe it's 0. So the minimum this one can be is -8. So then we want to know, okay, these are the minimum these things can be. What's the minimum prefix sum? Well, here it's -10. It's -10 plus -8, so -18 plus -8. Math, -26, I think. So we know the prefix sum of these things needs to be at least -26. So now we're going to place things in such a way, in such a way that we hit these prefix sum requirements for every position. What that means is if you did it on the first number of things, it would be okay. If you add one more thing, it still stays okay, right? We don't ever have an average that's too small. Yeah, and that's the entire problem. So we can just do that naively because everything's small. We have this dp, which is the number of ways to do it if we're at this position, and this is the prefix sum. And then we also have a bunch of prefix sum requirements, which I talked about earlier. So yeah, for each position, we just store what's the biggest you can place, and then also what's the smallest you can place. And the smallest is bounded by, you have to hit your requirement, and you also can't place anything smaller than 0. Right? And then you just brute force which thing you place, and then you store your answer. Awesome. Yeah, so that's my contest. I hope you enjoyed. Hopefully the solutions were helpful, and I don't know, I may have had an issue with showing the camera in the beginning of it, so I guess we'll see there. But yeah, thank you for watching. Hope you had a great contest. It looks like I gained some ratings, so I'm very happy with that. And now I have to go be productive with my life. So I'll see you in the next contest. And if you haven't seen the video where I built these, it's the last one on my channel, definitely go watch it. It's a great video. All right, thanks for watching, and see you in the next one. Goodbye.